When Einstein published the equation E equals mc squared, he said that energy and mass were basically the same thing. Little did he know that 15 years later, that fact would help him earn fame worldwide. That fame was not related to the equation E equals mc squared, but rather the fact that gravity could attract not only mass, but also energy such as light. Now that bold claim was a result of general relativity, and it is now called gravitational lensing. The theory of gravitational lensing has, for many years now, been an established theory that has been observed multiple times. According to Einstein's theory, the presence of mass curves spacetime. Now, light also follows a path through spacetime, so if it moves over curved spacetime, it will also appear to follow a curved path from our three-dimensional view. The only difference is that light is bent very little by mass, so even the Earth cannot bend light too much. The sun can bend light a little bit, but its brightness during the daytime outshines all the other light that would be otherwise visible. So gravitational lensing usually cannot be measured. But there is one exception. During total solar eclipses, deflected starlight can be observed, because the star's light bends around the sun before reaching the Earth, but the sun's light itself is blocked, and so the stars can be seen and photographed. In fact, that was how Einstein's theory was first confirmed. In 1919, a British astronomer, Arthur Eddington, painstakingly measured the deflection of starlight he had observed in an eclipse. In those measurements, which were in complete agreement with general relativity, were responsible for the acceptance of general relativity among scientists. But gravitational lensing need not happen around a single planet or star. In 1937, a man named Zwicky realized that besides stars, galaxies, and even clusters of galaxies could lens light. That realization has helped astronomers locate a number of gravitational lensing events. Now, a year before that, Einstein had realized an interesting thing about gravitational lensing. He noticed that light could reach a single observer from many different paths. Light from a distant source could move upwards before being curved downwards by a gravitational lens. Or it could move downwards and get curved up. Or it could move to the side and then get curved back towards the Earth. So he predicted that light would form a ring around the gravitational lens, caused by bending in multiple directions. Today, these rings are known as Einstein's rings. Einstein's rings are now regularly seen by the Hubble Space Telescope. Gravitational lensing and Einstein's rings are now commonly seen by astronomers, and they even play an important role in the study of another interesting prediction of relativity: black holes.